Hi you guys. So for this video we're going to cover parameterizing curves. So parameterizing curves conceptually, I'd like to just explain kind of what it is. I'd like you to imagine in your mind that a particle or some other object was moving in space. So our world is three-dimensional, right? And as an object moves in a path, it's moving through three dimensions, x, y, and z. In each of those, it's moving at different speeds, and generally its path is different in terms of each variable. So as you move into calculus 3, which is your next step, or beyond, as you look at how objects move, you're going to need to look at how they move in each dimension separately. So for this reason, we have this process, which is to take these curves that we can draw in the air that look like their path, and using a parameter variable, which can be angle or can be time. It can be frequently either one of those things, but also many other choices, just most generally theta and time. Using those as our input variable, we can describe these independent paths of motion. So that is where we are starting out. Okay, so thinking about that in mind, here's some general templates. You'll notice that in the textbook, in these kinds of problems, it mentions answers are not unique. What that means is that there's many different ways to parameterize the same curve. There's in fact probably infinitely many ways to parameterize the same curve. But we need to have a starting point, right? So the following are going to be my suggested templates for you guys to use. The textbook will use a different suggested templates. These are, like I said, these are my personal starting point. So let's take a look at what the circle template is. So to parameterize a circle that is going counterclockwise, what you'll do is you'll take your center, which is x naught, y naught, and your radius, which we'll use r for. And here are the following formulas that can parameterize it for you. So if you do x minus the center, x coordinate, equals r cosine theta, and y minus the y coordinate of the center equals r sine theta, that will give you that circle with the center and radius traveling. And the last part of the parameterization is you have to make sure to tell people what are the values for the parameter that we're plugging in. So the beauty of this is you can parameterize just parts of curves, you can parameterize the whole curve, you can parameterize traveling around the curve more than once, and all of that is controlled with your parameter variable. So make sure, even though it's easy to forget, to include this as part of your parameterizations. Okay, so let's say you want to generate the same circle clockwise. How would you do that? That's like going backwards. So we could start off with a negative theta in our parameterization, and then because cosine is even, cosine of negative theta equals cosine theta. That is a trig identity. And because sine is an odd function, you can pull the negative out. So you could use this parameterization here, or you could use the simplified version, and either one is going to get you your circle generated clockwise. Okay, so that is a circle, and here is the template for, actually an ellipse. I put a note here to remind me to tell you that for an ellipse, you can change the r's. So these r's, you can turn this into an ellipse by messing with these r's. So let's say you want, if you remember graphing ellipses from pre-calculus, you'll remember that there's like a major axis and a minor axis, and like an x radius and a y radius. So changing the x radius is as simple as changing this r, and changing the y radius is changing that r. So if they mismatch, that's when you're going to get an ellipse. And you can do the same thing with the thetas to give you the clockwise versus counterclockwise. Okay, so moving on to a line segment. If you have a line segment from x naught, y naught to the point x sub 1, y sub 1, here is the parameterization that I like to do. So I like to use binary with 0 and 1 to cover the entirety of that line segment, and I kind of use it as a switch. So I'll take my, notice that I mix and match, at x sub 0, we'll be plugging in t equals 0, so this term is turned on because it has value 1, and this term is turned off because it has value 0 getting plugged in there, canceling it. Same thing for the y, so you'll see the pattern of this will be turned on when t is 0 and turned off when t is 1. This will be turned on when t is 1 and off when t is 0. That is going to cover that line segment. Okay, and then for any other function that is a function of an input variable, so you'll frequently see y equals f of x or x equals f of y, if you let your input variable be equal to t, these are actually the easiest of all to parameterize. So we'll do an example of each of those together right here. Let's go ahead and start off with a circle. Okay, so let's say we're going to parameterize a circle centered at 1, -5 with radius 4 generated clockwise. So we have all the things going on with this, right? Let's go ahead and start with our template. So how I remember that template in my mind without having to just like have it written on a note card is I'll kind of remind myself from pre-calculus the Cartesian coordinates. So remember the Cartesian coordinates for this circle would be the following. Right, and just it's helpful to me to remember that because it kind of reminds me the pattern for what I'm doing for the circle, but it's not necessary. So remember the pattern is you just take your x and y parts that are in here, so x minus the center and y minus the center, and then you come and you do r cosine theta for the x and r sine theta for the y. So my r is 4, and it's going to be cosine and then 4 sine. And then last, we're going to look at how is it generated. Is it generated clockwise or counterclockwise? So because it's generated clockwise, that's backwards. So that is the negative theta one. So we could do negative theta there and there. And you can leave that as is, or you could kind of clean that up with simplifying. This is going to be equal to 4 cosine of theta plus 1. And this one's going to be negative 4 sine theta minus 5. Okay, and the last step, make sure that you're telling someone where the parameter is at. The parameter is from 0 to 2 pi. Okay, so if I were looking at this one like on a test, this would be the parameterization that I'm looking for. There we go. Let's take a look at this one on Desmos, and I will give you guys the explanation for how Desmos frequently deals with parameterization. So one thing that's kind of cool that I don't know if you guys have noticed, is that for Desmos, if you click on the 3 little bars here, it'll pull up some examples. And the cool thing about the examples is it tells you how to type things in. So I'll usually go down to the parametric introduction, and I'll open the graph, and what it's just doing is modeling how you type things in. So I don't need to see this direction, I don't need to see that direction. If I want to graph a parametric, just make each coordinate of the function t and then click on the domain to change it. So this is where I'm going to put my x equation. My x equation should be 4 cosine theta. Oh, and it should be, let's make it t to be consistent, 4 cosine t plus 1. And then negative 4 sine t minus 5. Okay, so let's zoom out. And then remember to change the parameter. It's going to go from 0 to 2 pi. Okay, now let's take a look at our circle. Our circle is centered at 1 right here, and negative 5 would be right there. And sure enough, that looks like the correct parameterization and circle. To make sure that this was graphed in the right direction, one thing that you can do is you can go in and restrict your range. So you could graph it from 0 to, let's go 0 to pi. So it went from here and it graphed this way down. And you can see that if you then restrict to pi 2, see how it's kind of going back in time. So I know that this one is in fact being generated clockwise. You can see it rotates around that way as you go. Okay, so we're done with the circle example. Let's go ahead and take a look at how we would parameterize a line segment. Okay, so let's say we were going to parameterize a line segment from 1, 2 to negative 3, 4. So my starting coordinate is this one. This is going to be where we're at t equals 0, and this is going to be where we want to be at t equals 1. So I'm going to take my x equals and my y equals templates, and I will put a t down, leaving myself a little space, and then I'll put a 1 minus t, and then make sure to keep the x coordinates. So 1 and -3 are going to go in the x equals equation, and I want to start at the point 1, 2. So you put the starting x coordinate on the 1 minus t term, and you put the ending x coordinate on the t term. Okay, same thing for the y. We put the 4, the ending, and the 2 starting. And then remind yourself this is from 0 to 1. Okay, so now let's hop on over to Desmos, check our parameterization. Okay, and then 4t plus 2 times, and we're going from 0 to 1. Okay, so looking at our point, let's make sure that our points are where we want them to be. We wanted to be at 1, 2, and -3, 4. Okay, and then let's make sure that this got graphed in the correct direction by restricting our domain a bit here for our parameter. So we'll go from t 0.25, then to 0.5, to 0.75. So it's clear that we are starting at 1, 2, and we are ending at -3, 4. Sweet. Okay, so we are done with the line segment one. And hopefully this is feeling a little bit less scary at this point. Okay, let's go ahead and parameterize just an arbitrary curve. So let's parameterize the upper half of x equals y squared, originating at 0, 0. Okay, so the upper half of x equals y squared. So x equals y squared is this sleeping parabola, is what we frequently call it. So what we're looking for is we want to get just this top half, and we're supposed to be traveling like that, right? So right away I can kind of tell that my starting curve is not a function of x, and I can also tell that from the equation. How? So from the graph, you can see it's not a function of x because it fails the vertical line test. Okay, so it's not a function of x, but it's a function of something. It looks like it's a function of y. How do I know it's a function of y? Imagine that you went ahead and grabbed this, flipped it 90 degrees, so y is viewed as more your input variable, and now, after you've done that, it passes the vertical line test. So this is, a matter of fact, a function of y. And so because it's a function of y, parameterizing it is not going to be hard. What you do is you take your x and your y, and you figure out which is your input variable. So because this is a function of y is the thing that's getting plugged in, and x is the thing that's getting outputted. So y is going to become my parameter. I'm just going to call y equal t. Now I'm going to come and plug t into my equation for y, and I get that x equals t squared. And because we just did a simple switch of y to t, I know that we had to start at y equals 0. So when we switched y equal to t, t must then have to start at 0. So when I tell people the parameter values, we're going to go from 0 to infinity to try and capture that whole upper half. Let's go ahead and check this on Desmos. Okay, we want t squared, t, and we're going to go from 0 to 1, then 10, then 100, then 1,000, and we can see, so on it, well, right now Desmos is like, you gave me too much to handle. But we can see that we need to let t go to infinity, and then we've got the correct curve. So there you go. Hopefully this was helpful to help you learn how to parameterize curves, and I'll see you next time.